Okay, so we're going to look at another area of a region here. So we've got two equations here. We need to think about the graphs of these. All right, so one of these is pretty easy. Y equals x minus 2. The graph of that is a line with y-intercept -2 and slope 1. So we can think pretty easily about what the graph of that looks like. This is just a little sketch here. This second one, or I guess the first one here on the screen, x equals y squared, may or may not be one you recognize. But if you can kind of relate that to the graph of y equals x squared, remembering that as kind of basic parabola vertex at the origin, this is really just when you think about inverse functions, you swap the roles of x and y. This is really the same idea. This one is not solved all the way for y here. You could do it that way and solve this for y and use your graphing calculator to help you get the graph. You do have to be a little bit careful about that though, that when you solve it for y, you remember a plus and minus so that you get both halves of this parabola. So if you don't recognize x equals y squared as this parabola that opens to the right vertex at the origin, just kind of the mirror image of y equals x squared, that might be a helpful thing to start recognizing. That's kind of just another basic shape of a graph that's helpful. All right, if you do solve it for y and graph it on your calculator, remember the plus or minus square root so that you get both halves of that parabola. All right, so I'm interested in the area of this region enclosed by these two graphs. So this region in here, and we talked before about that we can use a delta x or a delta y partition, and probably for this region you could actually do either. But one important thing to note is that if you do a delta x partition, you've got different functions defining the height on different parts of that region. So on this part of the region, I've got the top half and the bottom half of the parabola defining the height. And then on this part of the region, I have the top half of the parabola and the line defining the height. So while you could do this one using a delta x partition, the integration is a little more difficult, and you actually have to split it into two separate regions where that splits. Easier way to do this problem is to do it with a delta y partition, where you're dividing up this region this way and thinking about your rectangles going this way. And then those rectangles, using a delta y partition, those rectangles all have this parabola forming one side and the line y equals x squared forming the other side of those rectangles. So we're going to do this one using a delta y partition. The other thing that would be important about this graph, if it's not labeled and if you can't tell by just kind of thinking about the functions and their behavior, would be that you'd want to know these intersection points for these two curves. So again, you have a system of equations. You can think about solving this by substitution, perhaps. I have x equals y squared. So in place of the x in the other equation, I can put in the y squared. And I'd have y equals y squared minus 2. This is quadratic. Again, get it equal to 0. Subtract y from both sides. And this one factors. And when I set each of those factors equal to 0, I'll get y equals 2 and y equals -1. Okay, so those are the y coordinates of my 2 points here. I may or may not need the x coordinates depending on which way I choose to do the problem. It's not hard to find those x coordinates, just putting your y values, putting your y coordinates into the function equations here. All right, so I'm going to put them into this x equals y squared equation. When I have y equals 2 squared, my x coordinate is 4. And when I have y equals -1, -1 squared is 1. So those are the intersection points of my curves. Okay, so if I'm going to do this one using a delta y partition, then my integral is going to be done with respect to y. So I usually put this differential first. Put the differential first. And then that'll help you make sure you get everything else set up correctly. Okay, so the width of these rectangles is going to be from the larger, that would be on the right side, that's my line, we're going to call the line f of x, to the smaller. So when we're looking left to right, the smaller is going to be on your left, that's the parabola, and we're going to call that one our g of x. Actually, since we're doing this in terms of y, we need our functions all in terms of y, f of y and g of y. Okay, so I need my line equation minus my parabola equation, all in terms of y. Okay, you might notice that the line equation here is not given in terms of y. I have y equals x minus 2. But if I need that in terms of y, all I need to do is a little algebra here and rearrange that equation, add 2 to both sides, so that I have y plus 2 equals x. That's going to be my equation of my line in terms of y. Minus, and then I need the equation of my parabola that's on the left side. The line's on the right. The parabola is on the left side of this region. So the equation of my parabola in terms of y is y squared, x equals y squared. And then my limits of integration are going to need to be y values. So this differential here at the end will help make sure that you get your equations set up in terms of the right variables, also your limits of integration in terms of the right variables. Smaller one on the bottom here, lower limit of integration. My y equals -1 will be my lower limit of integration. And then my upper limit of integration here, my b, will be 2. Y equals 2. All right, from there, it's just a matter of tidying up this integral and then doing the antiderivatives, plugging in your limits of integration and finding the value here. So we've been working on that for a while. So we'll just go through that kind of quickly here. Antiderivative, 1/2 y squared plus 2y. Remember, we're finding an antiderivative with respect to y. Minus 1/3 y cubed, and all of that evaluated from -1 to 2. Putting in 2 first. So all of that minus my whole function evaluated at -1. Again, be careful with the parentheses and the negatives and the subtraction. So there I have my whole function evaluated at y equals -1. And now I just want to tidy this up a little bit. You can get out your calculator at this point, but be careful with all the parentheses and the negatives, or I tend to usually simplify a bit first. All right, so 2 squared is 4, times 1/2 is 2. 2 times 2 is 4. 2 cubed is 8. And then minus 1 squared is 1, times 1/2 is 1/2. 2 times -1 is -2. -1 cubed is -1, times -1/3 will be plus 1/3. And then if you want to go ahead and simplify or distribute the minus sign through, you can do that. Or at this point, if you want to get your calculator out, you can do that. You should get 9/2 or 4.5. Okay, so this was a good example of when you want to use the dy partition, dy integral for a delta y partition. You might also try doing this problem in terms of dx and doing a delta x partition and thinking about splitting the integral into 2 separate parts. You might do enough of it anyway to convince yourself that it's much easier to do it this way. The integration is a little harder when you do it as a dx integral, fraction exponents to deal with. And because you have to really do it as 2 separate integrals, you're doing kind of twice as much work. But you should get the same answer at the end. All right, do some more homework.